Hi, in this video, we're going to take a look at the steps that you take when you're doing a supervised learning model. Now, you talk to 100 different data scientists, you'll get 100 different answers on this particular topic. This is what I feel like reflects the emphasis of my experience working in industry. You talk to somebody else, they'll have a different opinion, different take on things. They'll change the order. That's fine. Our goal is to deliver a product, not to have some particular fixed in stone list. When we're doing supervised learning, we have a predictor variable and we have a collection of predictor variables and a target variable, and we want to predict or better understand the target variable. All right, so specifically, most of the time we're focused on making predictions on things that will happen in the future, or they could be for like channel assignment, like a project I'm working on right now. Could be for like looking back and understanding what happened in the past, which I started a project today on that. So there's a lot of different ways that we could go about working on supervised learning. All right, so here is the list that I've got. And I'm just going to run through all of these. This is, pretty exhaustive list detailing what's going on. Something I want to emphasize is that steps that are earlier on in the process are more important than ones that are later in the process. Okay, why is that? If you make a mistake early on, that's going to propagate all the way through. So imagine if I misunderstand what my stakeholders want, and I work through the entire project, and then my stakeholders go, hey, wait, whoa, you didn't do what I wanted. My entire project would have been wasted. Or maybe I would not have actually addressed what they truly wanted, and the math would be complicated enough that they wouldn't even know it, and they would be flying blind. They might be better off without my model. And so a mistake earlier on is worse than a mistake later on. All right, so something to think about that. If you could look at blog posts and videos on YouTube and people talking about machine learning, AI, stuff like that, there's going to be a huge emphasis on the tasks that are later in the process. So like the tasks that are going to be really like middle of my list. There's going to be a lot of emphasis on like model structure and tuning of parameters. Well, that's relatively late in the process. And honestly, from my experience, parameter tuning is not as important as your model structure, and your model structure is nowhere near as important as the data that you're putting in. And so making sure that you have good data is far more important than making sure that you have like a sexy model like extreme gradient boosting or k-nearest neighbors or logistic regression. Like your model structure is nowhere near as important as making sure you have good data. Garbage in, garbage out. Model structure will never overcome it. Parameter tuning will never overcome it if you have garbage in, garbage out. All right, so let's talk about the steps. So the first one is discuss the project with stakeholders, and I did that today. Going to be working on a project, and so need to see what does my stakeholder want, what data is available, what's the scope of the project, the timeline, and how much can they deliver on funds to make sure that I can execute this. Then pretty early on, and this was done during our discussion, was to identify potential predictor variables. At this step, this is going to be like your long list of predictor variables. Later on in the process, you'll start kicking out ones to get a better model. But here, it's kind of like you get every variable that could possibly be useful you have in this list. Kind of like everything in the kitchen sink gets thrown into this list. Now, depending on what you're doing, you might have to go out and collect your data. So if you're working in more of a classical statistics environment, you might have to actually go out and collect your data. Here, we would actually invoke design of experiments to make sure I have good solid data. Typically, as a data scientist, honestly, I'm going up to the database, I'm going to Snowflake, and I'm pulling out the data that I need. I'm really not worried about how the data got there or how it was collected. It's just there and it's taken to be fact and 100% correct, even if that's not necessarily a, correct. All right, so then so something will happen is data collection. So here, what I'm referring to is when we have to, go out and do measurements, collect our data, run surveys, stuff like that, and then store that data in a sensible manner so we can use it. Now, after my data is stored, so let's say it's stored in a database or it's stored in CSV, stuff like that, I need to actually get my data into my workspace to work with. And this can be a step that can take a really long time depending on how much data you have and how your system is set up. Snowflake right now at this moment that I'm filming is the sexy way to go for this, but I'm sure 5 years from now, another platform will be the way to go for your data. Now, the next thing we want to do, and usually we would want to filter as early as possible. That makes sense. We're going to filter out data points that aren't relevant to our project. We're going to filter out, outliers, anomalies, anything that could, have a problem. So if I can identify records that have just incorrect data and it's bad enough that it's not salvageable, then, that's like a lot of missing values or just flat out wrong values that don't make sense, then I can filter it out. Now here we're going to do feature selection. So here we're going to form our short list of predictor variables. Now you might do feature engineering first. You might do feature selection first. This is not like a hard fixed order. Depends on what your preferences, depends on your project, what your stakeholders and supervisor wants. Here I'm putting in, at this point, putting in your missing or filling in missing values. So filling in your missing values is a critical step to being able to get the most out of your data. If you take my data prep class, we talk about different ways to impute values and missing value patterns and missing value analysis. Here, I'm just saying you already understand that entire 2 weeks of material. Then we're going to do our feature engineering. And once again, that's a data prep topic. If you're interested in it, go to my data prep videos. Now, something that we're going to do is that we're going to partition our data. All right, we're going to partition our data into 2 or 3 sets. Either we're going to have train and test, or we'll have train, validate, and test. All right, so train and test. If I'm in a situation where I know my model structure and I'm not going to worry about parameter tuning, like I would with certain models. If I'm going to, like, let's say, use default settings or just the model just inherently tells me what the parameters are, then the training set is the set that I build my model on. The test set is the set that I'm going to use to evaluate model performance, model accuracy. All right, so why do we do it this way? Well, it works out. And you can take this as an axiom. All models overfit on their training data sets. All models overfit on their training data. The data I build my model on, my model will overfit to. All right, so what do I mean by overfit? There is always a difference between the data I have and the true overall population. I'm thinking about this from like a statistics point of view instead of like computer science or machine learning. All right, I have my data. My data is to represent the population of what's going on. So like if I wanted to understand the height of men in the United States, I could go out and measure a bunch of men, but I will never truly know what is the distribution of height of men in the United States. The data will approximate it. Now, there will always be a gap between the data's and like what the data says and what the true distribution is. No matter what I do, no matter how hard I try, I will never truly have a complete picture. I'll just have an approximation. All right, so my training data approximates a population that I'm going to be making predictions on. And so there's a difference between the two. The model only sees the training data, and the model is going to overfit on the training data. So there will be a difference between the training data's performance and the performance on the real life data that's coming up in the future. And so if I was to try to evaluate model performance with the training data, I will get optimistic results. Now, I'm not saying don't use those. I'm saying they will be optimistic when you look at them. And so the test set, what we do, I have training data and I have test data. I build the model on the training data, but then I use the test set, which was completely separate, not used for building the model, to evaluate model accuracy. And so then I get a more realistic estimate of how my model will perform in real life. Now, it's common to say that your test set is your honest estimate. I can tell you this from experience. Your test statistics will be better than your real life, model runs, like when you start actually launching your model. Expect the test statistics to be a little bit better than what you actually see when you launch the model. If the test statistics aren't good enough, then you need to go back and improve your model. Now, that situation I just described is when we're only going to build one type of model. I'm going to take my data, I'm going to build that model. It's already been decided. There's not going to be multiple models built. Let's say I'm in the situation where I have the flexibility to choose different models. Now, maybe your stakeholders aren't comfortable with a wide variety of models. Maybe you're going to have government oversight where you have to use a simpler model structure to make sure that auditors and regulators are comfortable with your output. Then in that situation, I'm going to probably use linear regression or logistic regression, and depending on the problem, and there is no flexibility on it. I don't need a validation set. Now, let's think about the other situation where it's no holds barred. I can do whatever I want to do to get the best prediction possible. So I could use lasso. Maybe I could use ridge regression, elastic net, neural networks. I could use random forest, stochastic gradient boosting, extreme gradient boosting, k nearest neighbors, support vector machines, quadratic discriminant analysis, linear discriminant analysis. I could do anything I want. It's just my goal to get the best model possible. Okay, so what's going to end up happening in that situation? If I do train, I'm going to overfit, and then I do tests. Well, let's say I just built 100 models, right? Just went through, built 100 different models, and I start running my test statistics off of that, using that test data. Well, what's going to end up happening is just off of happenstance in that test data, by how I just selected the data by happenstance, it's going to work out that there's some randomness that the model that comes out being the best may not necessarily be the one that is truly the best. And in fact, the more models I build, the more likely I am to have that problem. So how we can get around this is that we do train, validate, test. Okay, so I train my model on, I build the model on my training set. Then I use the validation data set to check model performance, check model accuracy, and I compare all my models, and then I use this as information to tell me which model should I actually go with. Now, after I've done that, after I've selected my model, then I'm going to use the test set to check model accuracy, and that's going to be my I'll say more honest estimate of model performance. And so we're checking model quality twice with validation and the test set. Validation is used to pick the best model possible. The test set is used to check what is a realistic level of accuracy that I'll get from my model. All right, so then after I partition my data, I'm going to train the model. Then I'm going to validate my model and select the one I want to use. So when I do that validation, there's actually two different ways. I could do a holdout validation technique, or I could use cross-validation, where I combine train and validate together and run through that. That's also in my data prep course, by the way. Then I'm going to test my model. And so it's important to make sure that when I validate and I test, the observations I use are not in any other set. So I've got 3 sub data sets of my total data: train, validate, test, and no data point is in more than one. Every data point is in one of the 3 is how we partition data. All right, now after that, if this is a real project that's going to have like millions of dollars of impact on your organization, you're going to start digging into your model and you're going to assess it more closely. You're not just going to go, okay, this looks good, I'm done. No, you're going to assess, where is it strong, where is it weak. I'm going to check the errors of my model, and I'm going to try to see, hey, is my model performing well on the extremes? Is it doing well when it should predict an extremely large value? Is it doing well with an extremely like large and negative or small value? Is it doing well in the middle, depending on what I'm working on? And so I'll dig in and get a more refined look at model performance. I won't just use the overall one number statistic. Then after I've got model performance assessed, we're going to internally vet the model. And so remember, I'm in a situation where millions of dollars will be decided upon based off of my model. All right, we're not going to just leave one person to just build a model and hope it's right. People are going to take a look at it, and we're going to do this internally initially. So we're going to share this with your boss, with your coworkers, with the people you're working with on the project, and we're going to double check, put eyes on it to make sure that everything seems right. We're going to do smell checks. Is like how I think of it. Where does the model pass the smell check? We're going to try and find flaws in it, find the strengths and the weaknesses before we move on. If things aren't up to snuff, then we go back to an earlier stage and start improving things. Once we feel comfortable with what we've got, we will present our model to our stakeholders and make sure that they are comfortable with the output, that it's accurate enough for them, that they have confidence when it's going on. The office I work in, we call it safe to buy. We want to make sure our stakeholders know that my model is safe to buy. Then we're going to put the model into a pilot phase. And so, remember, once again, millions of dollars being decided by my model. We're not just going to launch it and go, okay, that's it, we're done. No, we're going to put it into a pilot phase and let it run for a bit. If your model is replacing an older model, you'll probably have two going at the same time, and you're going to have the two models compared to each other to check to see which one's better. And so the pilot phase, frequently you're doing batch jobs, you're doing things more manually, and you're building up trust with your stakeholders that this is a good long-term solution for them. Then after that, we're going to formally launch the model. We're going to put it into production, and from there, like a lot of the heavy lifting is done. For my office, what's going to end up happening is I'm going to pass it off to somebody else to keep it in production. And I'm done building it. And then after that, we're going to monitor model performance and the input data. So here we're going to check, model accuracy over time, but we're also going to check, has the distribution of my input data changed over time? I had a distribution of my data when I built the model. Has that distribution changed? If it has, I might need to go in and rebuild the model and relaunch it. And then after that, maintain the model. And so there, let's say I see things, shifting, like I see some drift going on in my predictor variables, or maybe accuracy is not where it needs to be. I'm going to go in and maybe we completely rehaul the whole model. Maybe we go in and take more recent data and just, refine the parameters. Maybe we, choose a different model structure. It depends on what your office will want to do. All right. So I hope you've enjoyed this. Life is short. Do math.